All right, hi everybody. My name is Aldo Garcia, um, and I am from Michigan State University. I gave the talk on Tuesday on standard forms. So today I'm going to give a talk on Tomita Takesaki theory, where the main goal of this talk is to, at the very least, give you an example of a type 3 binomial algebra. Okay. So we start with a definition. So uh, a binomial algebra is said to be sigma finite if and only if uh, there exists at most countably many non-zero projections. And this is actually equivalent to M having a faithful normal state. So in here we don't have the triviality condition, which is pretty much what we're going to be taking away. So an example of this. So take a von Neumann algebra. Where H is infinite dimensional. And let Ci be an orthonormal basis of H, then the map X goes into this infinite sum of direct this infinite direct sum of vector states is a faithful normal. I'm gonna do faithful normal state on M. The faithfulness comes from all the xi's being an orthonormal basis, and normality comes from the fact that normality plays well with infinite sums, and each one is a vector state, so therefore um, it will also be normal. And I think I need to divide by 2 actually here. So this is not going to be 2. Yes. Okay. So the next thing is that we're going to fix a binomial algebra M with a state, faithful normal state. And following the procedure that we discussed before, when we were covering the standard form, denote
I mean, it's indoors.
Oh, sure.
Oh.
I've never been there.
denote the Hilbert space associated to the GNS construction by L2M of E. So in this case, we're going to keep running our state with us because this depends very much on the state that we assign. Then for X and Y and M, we have the same representation that we discussed before. So via um, and so as before, pi of v L2 of m. Well, pi of v. Let's do just pi of v. Pi of v is faithful, normal, normal representation. M. And then we identify m with its image so that we can think of m as a von Neumann algebra on B of the Hilbert space. Kind of ran out of space there. There we go. Okay, so the biggest difference that comes up for us is the one of the main tools that we use for the standard form was this J operator. So before that, I want to comment one more observation here. So note that one hat is cyclic and separating for M, and as well as the commutant. Okay. So let's define the operator that we want. So as before, uh, the map x to x hat, to x star hat, which we denote by f0, is not necessarily bounded anymore. So if you remember when the way that we went about showing that this map was indeed bounded was because we had triviality. In here, triviality pretty much forces us to note that this is going to be an unbounded operator, and so it means that we need to start working with unbounded operators. So sadly, I can't give you like a mini course on unbounded operators, but I can give you a few definitions, and we can talk a little bit about the discussion. In general, like for example, the differentiability, for example, is an unbounded operator that you have dealt with. So in here, so so when you're working with unbounded operators, because you can't use the entire because you can't define the operator entirely on H, you actually define it on some domain of S. Into H, where the domain of S is some subspace of H. Okay, so in here, the idea, I'm gonna bring it here, is that when you're working with these operators, you need the operator to be densely defined, which means that the domain um, is dense. Although you don't have any notion of continuity here, the best thing that you can ask for is closability or pre-closed, which means that when you graph the function, so when you look at the graph of this operator, I think it's, which is just C, S, and C. So you want to make sure that this is um, a closed set inside of H plus H2, and you also want it to come from some operator. But the definitions that we usually use is more sequential. So these are the definitions that people use sometimes to show that you do indeed have closeness and pre-closed. And then the other thing as well is that, of course, the other thing that matters a lot is the adjoint. But the adjoint, similarly to your unbounded operator, is not defined everywhere. So that's why you have this definition that depends very much. But you can see here that it's asking already for it to be at the very least to be an adjoint when you restrict yourself into the domain of the operator. Oh, this is supposed to be yes. And this is supposed to be yes. In particular, notice here that the pre-closeness, the condition is just that you converge to zero and you also already converge. So all you need to show is that the vector is in the domain of S, so that then you can apply S of eta, which would be will give you zero. Okay, so there's a theorem here that I'm going to mention, which says that S is uh, S is pre-closed if and only if S star is densely defined. So this is another way of being able to check pre-closeness if you know how the operator really looks like, right? Because if you know how the operator looks like, then you can look at what it has on its adjoints, and it allows you to say something about S. Okay, so I mean, I wouldn't bring this up unless we were going to use it. And so the idea is that S0. So um, note that S0 is densely defined since M hat is in the domain, pretty much is equal to, but let's just say subset. And it is also pre-close. Okay. This could be done in two ways. You can just use the definition, or you can be a little bit more um you can use the result above, or you could use the result above and show that M prime one hat is actually contained in the domain of S adjoint. And so my comment before where one hat is being cyclic and separating for both M and M prime will give you that S star is densely defined, giving you closability. Okay. So we denote the closure of S naught. Just the closure just means that, remember how I said, right? Like the idea is that the graph is closed and it's coming from a different operator. And so that operator in this context is going to be S. One of the main results from Tomita Takesaki theory which we won't be able to prove, is that so delta. So the idea here is that there's a lot of notions that extend to the unbounded case. For example, the notion of if the unbounded operator is self-adjoint, then you should be able to decompose it using what is it called again? Using a spectrum, you can decompose it. And then in this context, what I'm trying to write is the left and the right polar decomposition of S, right? So you should think of this as the positive part of the polar decomposition. Um, Notice that the map S0 satisfies the equation S0 S0 at x hat is going to equal to x hat, which implies that S0 S0 is equal to 1. This is going to be needed because one of the things that we end up getting is that um, J here is equal to 1. So in here, the conjugate linear isometry comes from the polar decomposition. And note that this is bounded, but this one's unbounded. Of course, if S is unbounded, right? The bounded operator. And then another nice thing that you end up getting is that JMJ is going to be M prime. And because this is an injective map, it means that 0 is not in its spectrum. And so in its point spectrum. And so you can write the operator delta to the IT of M delta to the IT. This is for all T. So in here, J is called the modular conjugation, and delta is called the modular operator. Okay, let's see. Nice. So notice that so we won't be able to prove this result. It is so lots some work to be done because you're working with unbounded operators, so you have to be very careful. But we'll just take this as a fact and we'll work with it. In particular, one of the things that this allows us to do is to define an action on M. So for each M, sorry, for each M, for each T and R, we defined sigma pt to be this, which is a star isomorphism on M. Since phi of t plus s is equal to phi of t composed with phi of s, phi of t is called a one parameter group of automorphisms. One of the things that Ekin had mentioned in Monday's lecture was that you can have an action in the space that will lift to the von Neumann algebra. And then you can then look at how that action in the von Neumann algebra, you can ask about ergodicity, freeness, and all of these conditions. But the idea here is that this analog of our von Neumann algebra being, when it's abelian being L infinity, there should be a notion of action. So in this context, we need the action to be some form of continuity. So one can show that T2 P of T is pointwise, strongly continuous. Which means for a fixed x and m, the map T goes to Pt of x is strongly continuous function. Because this is a map from S into M. So this is a map from S into M, and by strongly continuous, we mean that whenever you apply a linear functional, when you apply any element from the dual, this will be continuous as a real function. We call T the modular group, modular automorphism group associated. So our goal now is to show that well, not to show, but like to mention a result that pretty much tells us that the modular automorphism group is actually unique. So the characterization that categorizes its uniqueness is the KMS condition. So let T to P T. So this is just the general automorphisms, which are strongly continuous, and it's a one parameter group. Sorry, it's a one parameter group of automorphisms. on M on N, and V is a faithful normal state on M. And then V. So now the KMS condition is the following two. So the first one is so it's phi is invariant under sigma t, and the other condition is the existence of a of an analytic function. So for all x and y in M, there exists a bounded continuous function such that f is analytic, f of t is equal to t of x. So it's analytic on the strip here. Okay, so the next thing that we have is the theorem. So um, let P be a faithful normal state on it. Then P satisfies the KMS condition with respect to P with respect to the automorphism group, and if P is KMS with respect to another strongly continuous one parameter group, Pt, then they must be the same, given as the uniqueness. Okay, so the KMS condition here is pretty much allowing us to be able to switch the ordering of what it means to be able to switch an element from the left to the right. One thing to note here is that if x is well behaved, then phi of xy
is equal to phi of y sigma I to the x.
So by well-behavedness, I mean that this is well defined, right? Because we've only defined it for t, not really for just some any complex element. Okay. So one of the corollaries that this gives us is for x and m, the following are equivalent. So if you can show that this equation holds for all elements in X, then this is the same thing as A being a fixed point. Um, Although you probably don't know the definition, since I'm not sure how much was covered, the way you should be thinking about it is that R plus Rx on M through PT, such that P composed with P of T is equal to V. In other words, the uh, the action preserves the preserves the state here. You should remember this in the abelian case. I'm pretty sure I can probably comment it on this. So in the abelian case, for example, we had L infinity, x and mu, and you can then define an action by a group on X. Let's call it alpha. And so this condition at the end is pretty much telling you that alpha of S is equal to, yeah, the alpha of S is equal to alpha. So this condition above, the one that is coming from the state here, is pretty much telling you that it preserves the measure. Or it's measure preserving. So yeah, I have another definition we call MP. The elements in the fixed points. This is called the centralizer. And by the above equation here, note that, well, first note that this is a von Neumann algebra. So this is a von Neumann subalgebra of M. And the center of M is contained here. And this is just because of this equation here, right? So you can see that the equation, uh, this is just true for elements in the center. Okay, so I think we should probably go into an example. We've defined enough things. So let's keep it simple and let's look at matrices and with P being faithful.
fateful state.
Okay, so because of the fact that you don't need normality here, but because this is a state, necessarily this
It follows that phi is equal to the trace of some element. And the positivity of phi forces H to be strictly positive. H is in. This is mainly because Mn is a Hilbert space, so you can look at its linear functionals, which there's a one-to-one correspondence between the Hilbert space and its linear functionals. And so that's where I get H from. And then the positivity is just a computation that you can do. And then after by a change of variables, oh, sorry, not a change of variables, but a change of basis, we can diagonalize. We can diagonalize H. And the strictly positivity tells us that all of them are positive. We can always normalize this so that, well, this is a state, right? So it has to be normalized. So you can witness this. Another thing that because of the fact that P is a state, you should be having that the sum of lambda ones. So the sum of lambda k's is equal to 1. Okay. Um, well, I guess we should mention what the modular operator here is. So plain. Does anybody want to take a guess on what it should be? I'll give you a hint. Remember that remember how we define the automorphism group? We defined it by conjugating by the positive operator associated to the adjoint.
Okay, so you want to conjugate by H then.
Yes, exactly. Yes, yes. So it should be HIT. Well, this is a guess, right? Like we need to prove that it is. And the way that you go about it is using the theorem that gave us the uniqueness, right? So all we need to show is
I purely trusted your hint, so I'm gonna go with argument by authority.
That's a good one, but I can make mistakes. And so
Well, then it's your fault.
Yes, yes, technically that is true. So the idea here would be just to use the theorem that we had before, and we can just double check it. But yes, the hint was enough. This should be the trace of, and we can take away the yeah. So this is the trace of H HIT X H minus IT. But H and HDIT commute, and then this is tracial. So this is the trace of HX. So this uses traciality, which tells us that this is phi of X. Okay. The next thing that we need to show is to find a bounded continuous function that will be analytic in the strip that we defined. The good thing about this is that we actually know what H looks like, right? So
H is this operator that's diagonalizable. So H to the IT, oh yeah, I can write it like this. H to the IT is just all of these guys being raised to the IT power. Because of the fact that we need f of t to satisfy p composed with pt of x, y, it follows that this is the same thing as having, and I'm just writing the whole equation down, h 1 plus it x h negative it y. And so because of the fact that all of these numbers are finite, and there's not like an infinite sum, the function that we need to look at is f of c is equal to the trace of h1 plus ic x h minus ic, where c is a complex number. Well, technically it needs to be living on the strip, so the image such that the 0 is less than the image of c, which is less than 1.
Okay. And then this is just a routine check so that you can you need to compute. I mean, this is going to be this by computation by just plugging it in, but you need to show that f to the I plus t is equal to phi y sigma t of x. And in here, you'll use traciality again at some point. But the idea here is that because we're in this finite dimensional place, the operator, it makes sense to just extend this function. Yes, to just use this function. Okay, so one of the things that I mentioned while I was working on the standard form was the existence of a conditional expectation. In the case of a state, I want to give you also a characterization of when such a conditional expectation exists.
So let phi be a faithful normal state on M. Oh, by the way, this finishes this here finishes the fact that this gives us the claim, by the way. Just I feel like I should have said that. So yeah, okay, so let phi be a faithful normal state and let and be a von Neumann subalgebra. Then the following are equivalent.
Mhm. I should put faithful and normal. Yeah, okay, sorry. So faithful, not a faithful, normal, conditional expectation. En from M to N such that satisfying B composed with En is equal to B. And this is equivalent to phi being invariant under the modular automorphism group. So there needs to be some compatibility with the group automorphism. You can't just get it for free like we got it in the case of tracial von Neumann algebras. Right? And probably the question that comes up is
what happens if phi is tracial? Then delta is 1. This is because delta detects the non-traciality of your state, pretty much. And so you can go back and see the computations that we've done, and you'll see that delta appears because of this lack of traciality. And so this is also equivalent to saying that phi of t should be check. No. Yeah, this is phi of x is equal to x. Okay. So with the amount of time that I have, I think I should probably jump into the example that will give you a non-traceable Neumann algebra. Sadly, I won't be able to explain why it is a type 3, but at the very least, you can write it down. So the example that the example that I'm going to give you is similar to the hyperfinite to one factor. Okay? So it's going to be an infinite product, infinite tensor product. So consider two with phi lambda, where phi lambda is equal to, phi lambda is going to equal to trace normalize h, where x, where h is equal to 1 over 1 plus lambda. And here in a minute, I'll tell you what lambda is. Lambda 1 plus lambda 0 less than. So this is the conditions on lambda. Okay, so we do the construction of the hyperfinite. So M2 embeds into M2, tensor M2, embeds into M2, tensor M2, tensor M2. This is just by probably x tensor x1, tensor 1. And then you look at the algebra x1 tensor x2, tensor xp. And then you repeat 1 all throughout. P is greater than 0, and xi is in M2. For all I from 1 to p. This is, of course, a star algebra, and then the linear functional phi lambda. No, should yeah, this not should have been phi lambda. This should just be phi. Then phi lambda is going to be equal to x1 tensor x2. It's just the product of all of them. So phi of xi, the 1 to p. Yeah. Then we do the GNS representation. To give us a Hilbert space, H lambda, and associated to A and P lambda. And then uh the von Neumann algebra the von Neumann algebra closure. So WOT, the double commutant. This is the von Neumann algebra, R lambda, and and phi lambda and phi lambda extends to a faithful normal state on M. Yeah, okay. So when lambda is equal to 1, so if lambda is equal to 1, then phi is equal to 1/2 of the trace. Okay, so I should have not put normalized trace here. It should be the regular trace. So trace, and then this is going to be regular trace. Okay, then that just tells you that, and so phi lambda is tracial. And this procedure should just be giving you the hyperfinite to one vector. In every other case, is uh r lambda, p lambda are separable, hyperfinite. In the context of type 3 binomial algebras, another way to use it, or it's also called injective. Factors of type 3, which are called the powers. Factors. This procedure that we do here of tensoring keeps if each term that you're tensoring is a factor, it'll still be a factor. So we already know that r lambda is necessarily a factor here. But this is going to be a type 3 binomial algebra. Okay, that's all I had for today. Let me stop the recording.